Well, why don't we get started? Thank you all for coming. Good afternoon. My name is Kevin Chaffee, and I'm going to be the Master of Ceremonies for the 6th Department of Computer Science Undergraduate Research Symposium. And I'm going to stand up here with this microphone, which seemingly has no effect, but this is so that we can record this for posterity so that years from now, you can see the recording and say, oh my God, who is that guy who's introducing us? And you don't have to, all the presenters will get a copy of the recording, and you can delete those bits the second that you get them. So it's all good. So the format for today is we have 6 talks, and each one is going to go for 20 minutes. And whether or not some folks are doing this as a requirement to get honors. So for those of you who are juniors, sophomores, freshmen, you can do this too. What you have to do is sign up for 2 sections of Comp 396, do a project, write it up, and present it to your student colleagues. And some people are doing this just because they did an independent study project. And we let anyone who's done research in the past year talk about it. So some folks are doing honors, some people are just having fun. Actually, everybody, of course, just had fun. And to celebrate the work that everyone's done this year, after the symposium, we'll have a reception with refreshments of unspeakable awesomeness afterwards. So stick it out for hopefully 2 hours, and then we can have the fine refreshments. So the format will be each speaker has 20 minutes, followed by 5 minutes of questions. If you have a question during a presenter's talk to sort of clarify something, like did you really mean to say that, or what's exactly going on here, you can ask those. But if it's a more substantive question of did you think about this, what about this, or isn't this totally ridiculous work, save that to the end. Okay? So we'll do 5 minutes of questions, and then when the questioning starts for one speaker, if the next speaker would make their way up to the front and get their laptop set up, that way we'll just have seamless transitions, and no one will fall asleep because it'll just be non-stop excitement. It'll be great. So without further ado, I'd like to introduce our first speaker, Stephen Lowe, who's going to talk about Voronoi diagrams, which is work that he has done jointly with Professor Jack Snoink and his student David Millman.
Hey, I'm Stephen Love, and yeah, like Kevin said, I'm here to talk to you about Voronoi diagrams and some geometric transformations, some algorithmic precision, and an algorithm that Dave, Jack, and I worked on for computing Voronoi diagrams. So the first question on the tip of everyone's tongue is, what is a Voronoi diagram? And it's a spatial decomposition. So in the left, we have a 2-dimensional one. On the right is 3-dimensional. And you take that space and you split it up into regions called cells that make up the entire space. So what we do to create a Voronoi diagram is that we're given insights, which are special points in the region, and then we create cells from them that are based on those sites. And each cell is full of the points that are closest to the corresponding site. So everything that's orange is closest to site number 4, shown there. So what makes this cool is that it's been discovered and rediscovered by tons of famous people throughout history, and they all called them different things. My favorites would be plant polygons. And you can see how it would be useful, basically, anytime you have a space with locations in it, and you care about the distance to those things. So typical examples are post offices. If you imagine that this is maybe North Carolina, and we have a bunch of post offices, how do you know which one you should be giving your patronage to? You can look at the Voronoi diagram, and if you're in the one of these cells, the site near the center is the post office you should go to, and that's ignoring zip codes. Also, you can use it to find the biggest circle, or the point that's furthest away from all sites. So that's where you'd want to dump toxic waste, or possibly like build a new restaurant that's furthest away from all other restaurants. if you place sites on boundaries of obstacles, then you can use the Voronoi diagram for maximum clearance path planning for robots. So since the edges represent places where you're equidistant between two sites, that's where you're going to be furthest away from all the obstacles. And you can also use this for the Voronoi diagram can be dualed to Delaney triangulation, which is useful for making meshes and things. For the post office problem, I collected some real data of the trash cans in Citizen in the lobby. And I think this has moved since they did some reorganization, but yesterday they had 6 trash cans. And so, I always find it hard when I'm up near the top and there's 3 trash cans right next to me. I don't really know where to go. So thought I'd make a Voronoi diagram, figure it out for me. As you can see, we're here in the teleclassroom with the star, and you would think that we would all need to go to this trash can right here because we're in its cell, but there are a couple walls in the way. So you can generalize Voronoi diagrams to take care of these cases, but we're working with a specific one, which is the discretized Voronoi diagram. So instead of this clean image, we discretize it, put it on a grid with a U by U grid. So now we have pixels, and we want to find the site for each pixel that it's closest to. And this is MATLAB's documentation for its nearest neighbor transformation, which is a lot like the discretized Voronoi diagram. At the bottom, well, let's start at the top. The 1s represent sites, and then down at the bottom, the 7 and the 19 represent which of those sites is closest. So what makes our approach to this different? We wanted to consider the arithmetic precision required to calculate the Voronoi diagram, and this idea was introduced by Leota, Preparata, and Tomasia in their degree-driven analysis of algorithms. And the idea is that you would give the b-bit inputs, and you're going to need to do intermediate calculations. And if you don't have enough room to store all of those intermediate calculations, then some of the bits can be cut off, and you can't guarantee that your answer is correct. So, for example, if you want to test which site a pixel is closest to, you would approach it, standard distance formula. And if you put it in terms of the inputs, which are the coordinates of the pixels, then you can see there are some squared terms down here. So those require twice as many bits to represent. And so if we look at it, we can see that this is going to take twice the number of bits to represent than whatever you input. And we, following the degree-driven analysis, we want to minimize the amount of bits that it takes. So some of the past algorithms, Fortune's algorithm was the first in-log-in algorithm to compute the Voronoi diagram, and it has high degrees, 5 and 6, to query it. And here's a fun animation of it. Brew was the first one to discretize the Voronoi diagram and come up with a linear U-squared algorithm. Hoff et al. Was done here at UNC with help from Ming and Dinesh, and they actually use the GPU to draw cones that you can use to look at the Voronoi diagram. But the precision is hard to measure because it's based on the graphics processing's Z buffer, which is just like the resolution at what you're drawing. Maurer and Chan, they have a way easier to implement algorithm than Brew. And we came up with 2 new ones that we actually managed to get the degree down to 2. And this is important because that means that we can have inputs that are of single precision, like a 32-bit, 32-bit integer. And with a long integer with 64 bits, we can do all of the intermediate calculations without worrying about losing any bits. So here's some of the timing from experimental tests, because you saw a couple of these algorithms have U² time. So to actually see the differences, we ran them, and here's Chan down here and Maurer. And these are our two algorithms. We have U² and U² log U. The U² log U one, we had to, so Chan was degree 3, and we wanted to get it down to degree 2. For people who are interested in theory, we were able to make it only require U² time, but because it required a lot of randomization, it actually took more time to run than the U² log U one. But the reason that we have two different algorithms is because we first transformed the problem of making a Voronoi diagram to U different subproblems. So we solve it for each row. So of course, if you're trying to find which site a pixel is closest to, you want to minimize the distance formula here. And we can do some algebra, pull out a negative, so we want to start maximizing it. And then if we hold y constant, then this right side is all constant, and this changes with x. So to maximize, to find the site that maximizes this equation, you can actually represent it as a line. So over here on the left, we have our Voronoi diagram, and with the chosen row, we switch all these sites over to lines by this transformation. And then, since we're trying to maximize it, each, where the line is the highest line shows where the site is the closest. So if you see where the black line switches over to the purple line for the highest line, is exactly where they switch up here. So the upper envelope is now the problem we want to solve for each row. And generally, it's just the set of line segments that are higher than all the other lines, but we want the discrete one. So these dashed lines down here would be like the grid points. As you can see, this line doesn't make it in. We have a sample here and here, and that's how you can end up with non-continuous Voronoi diagram. So we're calculating our discrete upper envelopes, and they take the form, of a line, and the slope term only takes 1 degree of precision, but the y-intercept term takes 2 degrees, and we want to be able to do this in order U time with only 2 degrees of precision to get our algorithm to guarantee correctness. So there are a couple different ways to compute the discrete upper envelope. And the first is an algorithm that Chan uses in his algorithm. And you can take those lines and actually represent them as points. And when you find the lower convex hull, which is shown here, that actually represents the discrete upper envelope. There's also like a binary search, divide and conquer sort of algorithm that we can use. And there's randomization, which achieves the stats that we want, DOE that's calculated in only order U time and 2 degrees. But as you can see from this picture, it's really intimidating. It's hard to visualize. So yeah, Chan uses the lower convex hull. Our binary search is the one that's U² log U, and randomization is a little bit slower. So we want to figure out if we can minimize the degree of other geometric algorithms, or make a better way to represent these transformations so it's easy to tell what's going on. And Yep. Any questions?
Questions?
Mm-hmm.
Go ahead.
Can you name some real-world applications of these graphs?
Like finding the nearest post office. It's sort of it's a fairly primitive sort of thing. So if you had asked me why do we need to find the discrete upper envelope of anything, then I would say, we can use that as a small portion of solving a larger problem. So a Voronoi diagram might not solve an entire problem, but you can use it as part of a solution often.
Other questions?
Yes. What are some of the advantages of doing it discretely as opposed to continuously?
So computers are discrete. If you look back at Fortune's algorithm, it's less like the nearest neighbor transform, where it's like a grid, and so whenever you want to query it, it takes time. I don't know.
So I actually had a question related to that. Your density, when you're showing the running time, you have density on the bottom. Is that a function of the problem or the discretization? Is this the
That's number of sites in the. Yeah. So like, let's see if we. So like here there are 7 sites at the bottom. The density of that would, it's 5 by 7, so maybe 1/5. So density down here of up to half the pixels could be sites, and it doesn't make too much of a difference.
Was it expected that it would? I mean, it's because it doesn't seem to affect really any of the algorithms in any significant way.
Well, the runtimes are all like in terms of view.
I guess you have a log scale. But
Yeah, so the runtimes are in terms of view, and if they included in, then we would expect to see, because in is the number of sites, so that's what's changing with the densities.
okay. Well, thank you. Why don't you give Will the microphone while I introduce Will Hipschman, who I will be glad when he graduates because I don't think I've ever been able to pronounce his name right. So,
Do you want to learn right now?
I'm sorry?
I can teach you right now if you'd like to do it.
We can all learn something.
It's okay. It's hip, man.
This is Will.
Hi, everybody.
Will is going to talk about yet another animation system, and hopefully he'll explain why that's just such a catchy title, to harken back to the ancient days of research where every project started with the words yet another. Or someone's supervisor. But anyway, his supervisor was with the ever young Professor Dewan. Will.
So actually, somebody told me right before this that yet another animation system really lowered the expectations, so it made it easier for me to wow you guys by the end of the presentation. The reason we named it that was because there are a lot of animation systems out there, and compilers had sort of taken all of the names of saying yet another compiler or yet another compiler's course, and we decided that name really needed a place in animation systems, so we decided to own it for ourselves. My name is Will Hipschman, as he said. I worked with Prasoon Dewan for the last, 3 years on this. And Rebecca Crabb also participated in the early parts of this project, so I want to give a shout out to her here, and we'll do it again at the end. The first thing I want to talk about is what exactly animation is. In our context, we're specifically interested, at least for now, in animating data structures and algorithms. So an animation allows a viewer to see each of a series of updates to a graphical view of a data structure. So here we have a little view. We have a list of integers, and those integers then are formed into a bar chart. We have like these cute little rectangles, and you can go through and you can swap their positions and you can sort them, which is a pretty fancy thing to do. Now, animation is inherently difficult because there's a lot of different ways to do things. And so some of these hurdles are how do you do undo redo? How do you step through animation frames? How do you, if you have frames, how do you step through an animation language if you have that language? How do you allow users to have fine-grained control of what they're running? Another question is sort of what data can be animated. We just animated a list, but can we animate any data structure? If you give me some random data structure that I don't know about, can I animate that? If we look at this, we've got like a little clock here. So we have some date object somewhere, and we've got a little text box and a little second-hand thing that moves around the clock. And that sort of leads into the next question, which is how do we represent that data graphically? With this clock here, we've got the four shapes, the circle and some second hands, but we also have a text object, and you could conceivably only want the text object or only want the graphical objects. So there are multiple ways to display the same data. And the last sort of animation hurdle we'll be talking about today is how do we actually ultimately display those graphics? Do we have our own toolkit that does it? Do we just have like a list of shapes? Do we use like frame or swing's inherent capabilities? And that's something that somebody who's creating animations will have to decide for themselves as well. And a lot of us here are programmers. And so one of the things they teach you in introductory programming classes is that we want to be lazy. We don't want to have to do any of the work. And so, thanks Kevin for laughing at that. So it would be really nice if we could automate all of this work, if we didn't have to do any of it and the program would do it for us. And really the great thing is if it did all the work for us, if we didn't have to do any work, we could just sit at our computer and it would do everything. And so that's what I'm going to call full automation or automatic animation or fully automatic animation depending on how I feel when I say it. And in that case, what you'll have is you'll have some data structure here, a list, and you'll have some algorithm here, some sorting algorithm. And the programmer is going to say, hey, I want to sort my data, or I want to run this algorithm on my data. And the animation system is going to say, OK, and we're going to animate that, and you don't have to worry about anything else. And that would be really awesome. So we're going to work towards that goal. OK, so what do we actually automate? Because there's all these things that we can automate. We could talk about automating the undo-redo process. We could talk about automating the creation of graphics. We could talk about automatically being able to export and import different animations and run other people's animations. We could talk about different automations of pseudocode. So there's a lot of different places we can start here. And it can be very, very daunting. And in deciding where we want to start here, we also have to keep in mind that usually the more automation we have, the less flexibility we have. Because if we automate a lot of things, it means we might not be able to be able to control a lot of the other things. So we want a high level of automation, but we also want a high level of flexibility. We want the program to do most of the work, but we also want the user, if they decide to be able to use their own defined data, their own animation, their own graphical views of things. So we want to have a high level of automation and a high level of flexibility. We decided to start automating at the undo-redo level, primarily because it touches the least components. It's conceivable that you can create an undo-redo system that doesn't know anything about animation or anything. So that's what we're going to start with first. If we have our clock example here, we're going to talk about how we would actually build this a little bit. So we assume that we have some clock data structure, and every second that data structure is updated. And here we actually run into a problem pretty quickly. So assume we have some graphical view over here, and we have our clock data structure right here. If every time our clock data structure is updated, our graphical view is updated, we run into this problem where we can't undo redo because this is constantly being updated. Or we can't have the user control how fast they want to go through the animation because this data is constantly updating it. It's all up in the animation's business. So we really need a way to delay the execution somehow. And the way that we decided to do this is by creating a copy of the data. So we now have the programmer's data over here, our copy of the data, which I'll refer to as a copy or as a buffer. That copy's right here, and then we have the animation system or the graphical view of it over here. And what we also decided to introduce at this point is a way to delay execution by introducing command objects. So a command object is basically an object that has a target data structure and has a target operation. And at some point when it's executed, it runs that operation on that data structure. And they usually also have an undo or an inverse operation to be able to undo whatever operation they performed. So instead of updating the graphical view every time that the data structure changes, instead when the programmer's data structure changes, we create a command object and have that command object's target set to our copy of the programmer's data structure. Then, at some point in the future, when the command object is executed, our copy of the data structure changes, and the graphical view is updated at that point. So this allows us pretty easily to have delayed execution, which allows for users to be able to step through things. And it also allows for undo-redo, because command objects inherently have an execute and an undo function. So as long as the operation is invertible, we can step back and undo it and redo it as many times as we want. It also solves an efficiency problem that a lot of previous animation systems have. In the past, many animation systems would have a series of frames or a series of data copies that would take up a lot of space, which I guess isn't as always as important now because we have way more space than most of those ones that worked in the 80s and 90s did. But still, it's good to not take up space when we don't have to. So by using command objects, we're able to only have one copy of the data structure and a series of command objects, which is a lot less space than previous animation systems took up. It also allows us to, as I said, do undo and redo very easily, and it also allows for single-step and batch execution. So single-step execution is when a user says, okay, I click next, I want to see the next part of the animation. I click next, I want to see it again. And batch execution is when the user would click last, and it just runs through all the steps of the animation. You go all the way to the end. And so it's really easy to do this with command objects, because single-step execution, you just execute one command object every time the user clicks next. And every time the user clicks last, you just loop through and execute all of your command objects. So that's a pretty simple way to do it as well. And it also turns out that when we do it this way, we have sort of like two patterns working pretty well with each other. We have a producer-consumer relationship on one end and a model-view-controller relationship on the other end. So here we have the programmer's original data, which is producing command objects. And those command objects are being consumed by our sort of buffer copy object in the middle. And when a command object is executed and our buffer changes, it is then the model for our view, and it then updates the view as it changes. Here's an example of all this sort of working at the same time. We're going to shell sort that same list of integers that we saw earlier. And you can see they're flying up in the air in great, really hard to animate ways. And the user single-stepping forward through them. And in just a second, the user, I guess in this place, it was me because I took this video, is going to undo through them. So you can see they're now going backwards. So it has a full history of every state the animation has been in with only one copy of the data. And then at the end, I think we're going to step all the way back through to the end there. So you can see single step, undo, redo, and batch execution, which is pretty fancy, I think. So we're going to move on from here into what sort of data we can actually use with a system like this. And again, we want to make this really, really simple for a programmer, because somebody who's extending this system, they shouldn't have to do a lot of work. So we don't want them to have to worry about writing command objects. We don't want them to have to worry about creating a copy or a buffer. And we don't want them to have to worry about managing listeners or relationships between data, because that's really hard. I do this research, and it takes a long time. It's really hard, guys. And so the way that we decided to try and get around this was by requiring more information from the programmers, and by requiring their data to conform to programming patterns. Because when they use a programming pattern, it implies that there are specific undo and redo semantics to their data, which means that we can automatically create command objects for them. So some of the patterns that we currently support is a bean pattern. If you have setters or getters, it's implied that the set undoes the set. If you have an observer pattern, then the update undoes an update. And if you have a list pattern, then there's a bunch of different command objects. A remove undoes an insert, or a swap undoes a swap. And so by requiring users or programmers to use these patterns, we're able to basically generate all the intermediate components for them so that they don't have to do that. We also reduce the problem. Instead of requiring the user to create command objects, because we don't want them to have to worry about command objects, instead we say, OK, if you were going to be doing this by yourself, you'd probably be using model view controller, because you need a view and you have a model. So we can assume that you're going to be handling some sort of events. So instead of handling the events yourself, instead give us your events, and we'll create command objects for you. So we reduce the problem by making them use event handling instead of creating command objects. Here we've got just a little bit of code to show how an event changes into a command object. Every time a property is changed in a bean pattern, we catch that property change event and create a command object that would call the same set method on our copy of the object. There are some inherent trade-offs here, and we're going to go through those right now. One of the first cons is that the programmer does have to conform to a pattern, which means that their data can't just be some random piece of data, which is a restriction on what they can do. But realistically, that's probably a good thing, because their data should be conforming to patterns. It's usually good programming style, and if they don't know patterns, they'll learn patterns, which is, everybody likes to learn, so that's a good thing too. One of the potential problems is that it could be really difficult to debug. If any of you have taken Pursuance 401 class and used Object Editor, you know that if you have your set method spelled wrong, nothing's going to show up, and you're going to spend like an hour trying to figure out why nothing's showing up. And then you're going to email Pursuant, and he's going to be like, your set method spelled wrong. So in the same way, if you use a pattern incorrectly, if your method signature is wrong, our program might not recognize it, and it could just ignore it. Now, that's offset by the fact that the programmer is writing less code by using the pattern. When they use this pattern, they don't have to do any of the copies or the buffers or the command objects or really any of that event handling at all, which means that there's less code for them to get wrong, which can offset that a little bit. And one of the other trade-offs is that we allow a programmer to define their own data and to write their own sort of custom copies and command objects if they want to, which can be very difficult and time consuming, but it allows them to basically extend our system in the ways that they would like. So it's not a very frequent case, and because of that, it's a little bit more difficult, but it is possible. So we've talked now a little bit about an undo-redo engine, and we've talked a little bit about different data type support. But we're going to talk a little bit now about how to actually get a graphical display showing up. Most systems in the past supported like 10 shapes. They said, here are the 10 atomic shapes that you can use, and you have to use our shapes, and if you don't want to use our shapes, too bad. We said, OK, we can make that a little bit more broad, and you can use shape patterns. You can say, if our object looks like a shape and it behaves like a shape, we'll treat it like a shape and display it like a shape. And so here you see an interface for a point that has x and y properties that we could have the programmer implement themselves. So they can have their own implementation of shapes, which if they conform to patterns, we will recognize them. And ultimately, we decided that it would be good for our system to end up with a list of shapes. So our animation is going to consist of a list of shapes that are changed over time, because that sort of makes it not coupled to any sort of graphical display or any sort of system. So it's a pretty easy way to do it. So here we can see you've got some layout manager that has a display function that takes a data type and returns a list of shapes. And here's the implementation of that for our really fancy bar chart example that we've been going with so far, where you see it takes a list of integers and it converts them to rectangle models and it displays them on a screen right here. So that's how data is transformed into shapes. But we also have to think about how those shapes change when the original data changes. And in order to handle that, we've basically created trappers so that take an event from the original data, well, not the original data, in this case, our copy of the data, and they take that event and they transform that event into some graphical change. And so here you've got a lot of code for a event handler for the list of integers we have so far, where you can see it gets the two shapes and it gets their x positions and it swaps them graphically. And here you've already seen this animation, but this is, if I can find my mouse, there it is. This is just the animation for the trappers and the layout manager that we just saw. It's important to look at how events are actually processed in our system as opposed to in other systems. A lot of other systems have tightly coupled code and animation code. So if I were to write a data structure, I would stick animations in that data structure that correspond to the animation. Or if I was writing an algorithm, I would stick annotations that map to some text file somewhere that correspond to an animation. This is bad because if the programmer wants to change the algorithm or change the data, they're forced to rewrite basically everything. They have to create new annotations. They have to create new files to show how those mappings take place. Whereas in our system, events are coupled with data structures. And so in that way, algorithms are able to share events. A bubble sort uses the same events that an insertion sort uses, which uses the same events that a randomization algorithm uses, which makes our system a lot more modular in that if I want to change something, I don't have to change anything except the algorithm I'm using. So here we can see, we talked about automatic animation earlier. We're going to see our shell sort example, and we're going to see, I believe, an insertion sort example. And both of these have identical code except for the algorithm that's running. So you can see that the user, or the programmer, all they would have to do is say, hey, here's our data, here's our algorithm, let's run it. And the animation system will automatically generate the algorithms based off of that. OK, so one of the common applications of animation systems is as a teaching tool or as a presentation tool. And as a teaching tool, it's important to be able to show an animation alongside the pseudocode that it's actually running with. It provides like a dualistic method of learning, which apparently is a thing that they use nowadays, where you can basically say two representations of the same thing to help you learn it better. And so we wanted to be able to provide some sort of pseudocode support. So we asked ourselves, can we provide pseudocode support, or do we provide actual code support? And with our systems, it's impossible to actually provide actual code support because we don't know anything about the code that's running. We only know about the events that are being fired from the programmer's data. And so it made sense to us, and it was easier for us to provide pseudocode support. We also talked about sort of how we would bring the pseudocode into our program. And we talked about file I/O and decided that was kind of clunky and that the programmer shouldn't have to deal with handling file I/O or knowing what the file's name was or worrying about exceptions. So instead, they have some pseudocode in a file somewhere, and they tell us where that file is. And on the fly, we create a class that transforms that pseudocode into a list of strings. That way, the programmer only has to deal with a list of strings as opposed to a file, which is a lot nicer as a programmer to deal with. Now, one of the problems with our system is that we can't intuit how the mapping from command object execution to pseudocode should take place. And that's because we don't know really anything about the pseudocode or the actual code. We just know when commands are executed. So we require the programmer to provide a mapping so that we know how to do that. Other systems that couple the code and the animation system might have more knowledge of the code, and so they can do this potentially better than us, but they do not have the capability to do automatic animation because of that coupling. And here's an example of that actually running. We're going to run a bubble sort on these vertical bars over here, and we're going to run through the end, and you can see it's highlighting the pseudocode as it goes along. And if you step through this single step, you'll be able to see every step of the pseudocode running, and potentially use it as a cool tool in terms of learning data structures or algorithms. In conclusion, I'm going to draw attention to the modularity of our system, and I'm also going to sort of compare it to some of the other systems of the past. One of the big things that we wanted was all of our components to be separate. So we started with this undo-redo engine right here that knows about command objects, and it knows about single-step, undo-redo, and batch execution. But it doesn't know anything about data types. It doesn't know anything about data structures or patterns or graphical views. So it's completely separate and could conceivably be used for an application that has nothing to do with animation. On top of that, we provide data type support, which knows about patterns and knows about data, but doesn't know anything about how the data is actually being displayed graphically. And on top of that, we hit the graphics, where we're able to show what it looks like graphically. And on top of that, we say, OK, you can use pseudocode or you can use no pseudocode. And then on top of that, we say, OK, you have this list of shapes ultimately. How do you actually want to display it? In our system, we've used Object Editor, which is a program that Prasoon Dewan makes that allows us an easy way to display shapes. But any other toolkit or any other system could be used. We don't restrict how you actually want to display that. And so if a user or if a programmer wanted, they could use completely built things that we've already provided, and they could use this left side over here. Or they could say, OK, we're going to use your undo-redo engine, but we want to define our own data, and we want to make a custom animation, and we want to provide pseudocode support, and we want to use our own toolkit to display it. So they can really pick and choose which pieces they want to use. Here's some evaluation dimensions, and I want to call attention here to the undo-redo approach that we use. We use command objects, which is a more classic undo-redo approach and solves a lot of efficiency problems for animation systems. And I also want to draw attention to our user-defined data and the fact that we're the only system that does fully automatic animation. Thanks, Kevin.
Just going for a stroll. Questions for Will? I think they're all digesting it. Well, Ren, why don't you come on up and get yourself hooked up? Thank you, Will.
Thank you so much.
So we're gonna move on to Ren Bauer, who's going to talk about SIML.
Yes.
You pronounce it? SIML, a template language for an extensible data-driven decision support system to support policymaking, and this was supported by Professor Hai-Chung Kong.
Thank you. Hey, everybody. Yeah, SIML, it actually stands for SAS Internet Markup Language, and I'm just going to give you a little overview of what it's for and what it does and how it works. So as I outlined, the first thing I'm going to talk about is what a decision support system is. There's a couple different types. I'm going to talk about active versus passive. I'm going to talk about data-driven versus model-driven, just as some examples. And we'll talk about the related work and the design of the DSS and what kind of DSSs have already been made to support policy making. Then we talk about SIML itself. I'm going to talk about, like I said, what it's for, what's it look like, and what it does. And finally, I'm going to talk about some future work and take some questions. So what is a DSS? And it was defined in a really cool paper in like 1950 as a computer-based system to support decision-making. And it basically consists of three parts. There's a database, a model, or a decision context, which is kind of the data-driven equivalent, and I'll talk about that more later. And then obviously there's a user interface. And so a little bit of taxonomy. There's a couple ways to classify DSSs, and one of those is by how it works with a user. And so there's passive DSSs, which provide information to the user to help them make a decision, but they don't actually offer suggestions of solutions. And then there's active ones, which provide the information and then also provide suggestions. And there's cooperative systems, which provide information, provide suggestions, and then take user input on those suggestions to improve their suggestions and provide new ones. So another way to classify them is by what kind of drives the DSS. So there's communication-driven, which an example of that is like Microsoft SharePoint. And then there's data-driven, which is what our system is. And basically, that emphasizes a time series of data. So you have a bunch of data sets over time, and you're allowed to look, and it helps you look at how that data has changed and what kind of things have affected that data. And then there's document-driven, knowledge-driven, and model-driven. And these are basically the two that we're going to talk about, because a lot of research has been done in the model-driven area, especially with relation to policy support. And so related work in policy support, most of the DSSs in this area rely on models. So an example of that was a 2010 study done on Bangkok on what's called LEAP, which is the Long Range Energy Alternatives Planning System. And what this did was basically they set up this model to work in Bangkok, and they wanted to know what kind of policies they can implement to reduce the growth in their energy demands over the next several years. And what happened was this system actually provided 16 solutions, and they discovered that the most significant energy savings would be in the transport sector. And some advantages of using a support system like this is that they can provide suggestions, which is great, and it's backed up by real math. So for example, here's a graph where the dark black lines were the projected uses with no changes. And then the lighter gray ones are a couple of the solutions offered by the decision support system and their projected energy uses implementing those solutions. However, some negatives of this approach, it can be really difficult to adapt a model to a new situation. It takes kind of a lot of input, and it can take a lot of technical savviness to use. And then also, there are a lot of situations in which a model may not fit, especially something like us, we work in social work. And so it's an environment that's rapidly changing, and you might not be able to put that in mathematical terms. So another area where there's been a lot of related work is DSS design. Unfortunately, we found that a lot of the research done in this area was actually, although it was actually done for model-based systems, it was very applicable to data-driven systems. So for example, this is a figure that shows the kind of users involved in the design system. And the three main users are IT specialists, end users, scientists, and then there's also an architect, which is kind of the overseer who needs to understand everything. And in this example, the scientists are basically the people who come up with the model. And we found that in our situation, although there isn't a model per se, we still need to have scientists that decide how they want to look at the data and what kind of views they need. And so you can kind of think of our model as how we display the data, how we sort the data, and how we allow the users to look at it. Next figure shows kind of the iterative steps. And so I'm sure some of you have seen this as kind of the active design that we talked about in software engineering. And basically, the user says, I need a software that does this. And then science comes in and they says, OK, well, we have this data. We can display it this way. And how does that help you? And then it takes you to the IT people who actually implement it. And then it goes back to the user who say, that's not exactly what we need. And I've experienced this firsthand. We do demos with the social work people. And they say, I like this graph. I don't like this graph. What can you do to help me out some more? And then this figure here shows kind of the 8 steps involved in building a DSS from start to finish. And we found that this is very similar to the 8 steps we went through and are still going through. With the exception, it may seem that model selection and model integration aren't really applicable. But as I said, that still applies to how we decided to display the data and what data we decide to use. So that brings us to SAS Internet Markup Language itself. And what is it for? And so basically, we're working with social work people, and they have a lot of data. They have data on child welfare, food and nutrition services, and work first are just 3 sections that we facilitate. And then we also have some census data and other things. But basically, the root of the problem is that social workers needed a better way to look at this information and to extract useful information and use that to support policy making. And so this brings us to what it looks like. And these are some screenshots of our website, which is built using Simul. And you can just see this is a table we've created and a couple different types of graphs. And this is actually a PDF output, which we support exporting from the web into PDFs and CS and common separated value sheets, which can be opened in Excel or whatever. And so that brings us to how it works. And basically, the Simul environment comes with 3 major sections. There's template files, external files, and compilation engine, and the compilation engine. And we'll talk a little bit more about each one of these at the next slide. And so how the user does is they make a configuration file, which is written in Syml, which is an XML-based language, and they specify which template they want to use, what kind of data set they want to pull data from, which variables they want to use, how they want to display it, and all sorts of things like that. And the user runs this compilation engine on the configuration file, and basically that takes the configuration file, combines it with the template, and produces one SAS Internet output file. And then finally, they just go and open that up in a browser. And when that happens, the output files is combined with the external files, which are just other SAS Internet files. And those are rendered to HTML and displayed to the user. So this is kind of an overview of that. Sorry. You got your Syml files and your template files. And when you run the compiler, it takes those two and combines them. And as you can see, there's a bunch of template files, but you choose only one. And that gives you one SAS Internet output file, which when viewed is combined with external files to produce an output. So this is an example of one Syml file, and as you can see, it's pretty short. Basically, what you've got going on at the top is you set the title for the web page or the display. You establish some variables, for example, what you want the data set, which data set you want to use, which variables you want to use from it, what you want the labels to be on the graph. And then you have a section here where you can put in whatever code you want. So in the template file, there are basically a bunch of different areas where you can add code if you want to. And you can add any type of code, you can define variables, you can do whatever you want in those areas. And that's an example of one of those. And then here, this is an explanation of the chart. As you can see, that actually takes up a lot of the file. But there's not really any other way to do that. And so after you run this through the compilation engine, you end up with a file like this, which as you can see is a lot bigger. And this is basically a combination of this input file and one of the template files. In this case, it's a template file for drawing a pie graph or a bar graph. It supports both. But this is really just one step in kind of a three-step process in taking a Syml file and turning it into final output. You run through the compilation engine, and you end up with a SAS Internet file. And then you have a broker, which is on your server, which takes that and converts it into an HTML file, which then the browser then turns into final output. And what you end up with is something that looks like this. And so the different parts of this website are basically this whole chart area here, which comes directly from that Syml file combined with the templates. And then you have the menu here, citations and things like that. And the general look and feel of the website is more designed by those external files that we were talking about. And so some advantage of this system is that it's very extensible. It's really easy to go into this system once it's established and add a new page. Say, I know our website, we started out with just one type of data, and over time, we added the other sections. And then usability. Our goal here was to create a system where someone from social work who doesn't have a lot of background in computer science can say, I would really like to make a web page where I can view a graph of this data. And they can come in, write a short configuration file, and then have their output, a little while later. And then that brings us to future work. So some things that we still need to improve upon are adaptability. It is great once you have a system set up, it's really easy to extend it, but it still may be difficult to move from one location to another and implement an entirely new system. And so some things we need to do to accomplish that are to make it more easy to modify, like the look and feel, those external files, and to create new templates. And then user personalization. There's been a lot of research in DSSs around customizable menus and systems that will get to learn to know their users so that they can provide them with better support. And then finally, more active support. Like I said, one great thing about models is that they are able to provide suggestions for solutions when you're struggling with a problem. So an example of how we might be able to implement this is to integrate some policy data into what we are already giving people. So for example, say you're working on a PowerPoint presentation and you just want to peruse the work first data of your favorite county, which happens to be Brunswick in this scenario. And Syml notices for you that lately you've had an increase in your work first cases. But it also knows that in Ashe County, they've had a sharp decline since they implemented WF 9000 in 2011 Q1. So you might want to check that out. So you can click there and it might bring up the graph from Ashe County. And it might give you some details on that policy WF 9000 that it was talking about. And that might be able to help influence any suggestion you might make for future policy in your own county. So just to recap, what a DSS is it's a computerized system to help people make decisions. And we found a real need for something like this in in policy making, where they have a lot of data and not a lot of good ways to view it. So we saw an example of a model-based system, which provides good support, but unfortunately isn't applicable to all situations. We looked at the design, and we saw how a lot of the research done in the design of DSSs is applicable to data-driven as well as model-driven. And then we looked at a system that we've developed, which takes a simple configuration file and turns it into a very usable graphical output. And then we talked about future work, where we might be able to involve a more active interface with a system such as ours. And that brings us to questions.
Great. Questions for Ren? So how much content has been authored in Simul?
Well, you can see this whole webpage. We have basically 4 big sections, and then each section has, I don't know, the size exactly. HiTrack might be able to give you a better scale.
Just you guys have done.
Yeah.
So if anybody wants to find out anything about child welfare in any county in North Carolina, you can go to our website. We have about 10 years worth of that, and different views. So whether what kinds of what the racial breakout is for children in welfare or not, that covers 3 programs. So food and nutrition is a food stamp program. So there's 3 programs. So if you're a county person, county DSS, trying to figure out how to use your budget better, this is the kinds of information you need that's not easy to get.
I guess I was just more wondering if people have used it besides you guys.
Oh, actually, this is used. We have about 500 hits weekly by the county.
But in terms of authoring.
Yeah.
I mean,
Yeah, we have somebody actually at social work. This was done
Excuse me.
manually, and so Ren built that compiler. So we had somebody at social work do some of it, but I was writing most of it because I was the only programmer, and I got Ren to do this so that now I can actually have social work people who are somewhat trained in writing XML code, who knows HTML to do this. And we've got one other person who's trained to do that.
good. Well, thank you, Ren.
Thanks. How do you do what?
Okay, so next up, we have a trio of networking talks. The first one is about modeling UDP traffic for fun and profit. And this is because these 3 they're going to present were all part of a grant by the CRAW, so they actually made money. And of course, by default, they all have fun. And so again, Rebecca Crabb will present modeling UDP traffic, and she was supervised by Professor Eichert and by some guy who's trying to look more distinguished than he really
I
is.
have to change it so that it's extended.
It's fine. It's fine. Figure this out. Yeah, I got it. Okay. Is that working? Okay. As Dr. Jaffe said, I'm Rebecca Crabb, and I've been working in the networking lab with Dr. Jaffe and Dr. Eichert for the last year. And the title of my talk is Modeling UDP Traffic. So a brief outline of what I'm going to talk about today, the goal and significance of my research, some networking background, my thesis, methods, results, and then future direction for my research. So the goal of my research was to analyze and model UDP network traffic at the application layer. And this is significant because when running network experiments, we need to be able to regenerate realistic application traffic. And currently here at TCP, or here at UNC in the networking lab, they regenerate TCP traffic and can model that realistically, but they just ignored UDP when they did this. And it's also important because although UDP is a much smaller percentage of network traffic, it does not implement congestion control or flow control. And because of this, in the early days of the internet, people were worried that streaming applications that used UDP would destroy the internet. So understanding more about UDP and how to model it and regenerate realistic traffic is important for running these network experiments. So for a brief background in networking, network can be broken down into a protocol stack, and each layer implements a different function. And each one uses the functions of the layer below it as like a black box. It doesn't know how it implements its functions, and it doesn't need to know it. It can just use it. And the 2 main protocol layers that my research dealt with were the transport layer and the application layers. And so the two main transport layer protocols are TCP and UDP. TCP is a point-to-point full duplex protocol, which means that packets are sent in both directions simultaneously. It's also a reliable protocol, and everything is guaranteed to arrive in order. And it does this using sequence numbers and ACKs. TCP is also connection-oriented, which means there's a handshake, which is a few packets sent back and forth before any actual data packets are sent. And as I briefly mentioned earlier, TCP implements congestion control and flow control. UDP, on the other hand, guarantees nothing. It doesn't guarantee that everything you send gets there. It doesn't guarantee that it arrives in order. It doesn't have sequence numbers, so it can't do that. And it doesn't even establish a connection. It just starts sending data. And these differences can be visualized in these packet headers. So here's an image of the TCP packet header. You can see that there's sequence numbers, acknowledgement numbers, a window size that's used for flow control, and a lot of other data that can be sent in the header. And compare that to the UDP packet header, which basically has the source port and the destination port, and then the data. So where it's coming from, where it's going, and what you're sending. And so in order to model UDP, we decided to first look at how TCP was modeled here. And TCP was modeled at the application layer, which means that it was a network-independent analysis. So they could model and regenerate TCP traffic and run experiments while changing different parameters in the network and still have realistic application workloads. In order to make this model of TCP, they used their knowledge of application protocols behaviors. So some of these applications that use TCP, some of the most common ones are HTTP, SMTP, and FTP. And all of these protocols have what's called a request-response structure. And in this structure, you can see evidence of an epoch structure. And an epoch structure, as you can see here, is so this would be like a client-server connection, and the A1 bytes would be the request. And so that would be multiple packets grouped together into one chunk of a request. And then the server would respond with B1 bytes, which would be the response. Again, a group of packets sent all at one time as fast as the link would allow, send the response. And then there's time in between, and then you get another request response. And so those are broken down into what's called epochs, or what are called epochs. So originally we started modeling UDP and even trying to regenerate the traffic, and we modeled it just like we did with TCP. But then once I started digging deeper into analyzing UDP, I realized that modeling it just like TCP probably wasn't the best idea. So then we decided to look into how we could determine whether or not UDP exhibited this epoch structure like TCP. And once we determined what to use to determine that, come up with the answer of, does it exhibit epoch structure or something else? And if it's something else, what is that? So I decided to take the similar approach of TCP and start with UDP at looking at the applications. And so the main use of UDP is in real-time video and audio streaming applications. And then there are two other applications, the DNS, which translates host names into IP addresses, and DHCP that also use UDP. And these real-time video and audio streaming applications use UDP because of its unreliability. If you lose a packet and you lose a frame of your streaming video, most users aren't even going to notice. But if you use TCP and you had to wait for the ACK to never return and resend your data, you'd be buffering and nobody would be happy. So with the knowledge of how applications were using UDP, we then decided to look into the network data and the actual packets themselves. And to do this, we used a tool called TCP dump. And TCP dump captures packets at the network layer, so TCP and UDP packet information. And it captures this data in both directions. And the data that I used to analyze UDP was taken over an hour-long trace here at UNC in 2004. So I started out by writing scripts to parse this UDP connection data. And when I refer to UDP connections, as I said earlier, UDP doesn't actually have connections. I'm referring to a for tuple of the same source and destination IP addresses and port numbers. And then I graphed this data over a 30-second interval to get a snapshot of the patterns of these connections and what was going on. And I graphed many of these graphs. This is 50 random UDP connections. Along the y-axis are the different connections. So every horizontal line refers to a connection, and the green and red packets are the two different directions that the data is traveling. And so you can see here that, well, it might be hard for you to see, but if you analyze these closer, and I have multiple of these graphs, in all of them you see this evenly spaced out pattern where there's a few packets along the whole time with a very even space in between them. And so this led us to think that maybe the epoch model wasn't the best idea, and to look into this further. And so to analyze this in more than just a visual snapshot approach, we decided to look into inter-packet times of each UDP connection, so the time in between seeing packets sent. And so I wrote scripts to calculate these inter-packet times per each connection and graphed CDFs of these, as well as calculated some different statistics. So here's one CDF of UDP inter-packet times. As you can see, this vertical line means that all the packets, 100% of the packets of this connection had the exact same inter-packet time. And not only was it the exact same packet time, but it was 65 seconds, which is a huge time in terms of inter-packet times of connections. And this is a trend that we saw. Again, this is one CDF, but we have 30 of these, and this is a trend that you see throughout all the graphs. So here's another example of a inter-packet CDF, and we have two different very vertical sections in this one. So about 70% of the packets had the similar inter-packet time of about 0.02 seconds, and then 30% of the packets had, again, a much larger time, about 500 seconds, but again, a very constant inter-packet time. And here's just another third example. This one has a lot more packets in the connection. There are thousands of packets in this graph. And we, again, have two different distinct vertical sections. These times are more what we would see in TCP, around 0.25 seconds. They're still a little bit larger, but 0.5 seconds inter-packet time. So then in order to compare this to the TCP and the epoch model, I did the same thing with TCP inter-packet times. And again, here the green's in one direction and the red's in the other. And you can see with this green direction that there are a lot more packets with very small inter-packet times and with more variability than we saw in the UDP graphs. So about 50% of the packets there have varying times, and they're within, they're between 0.01 seconds and smaller. And this would make sense for our knowledge of the epoch model for TCP, because they're sending a big chunk of data, multiple packets, as fast as they can, as the network will allow. So you would expect to see very small times, but with no uniformity, because they're not worried. TCP is not worried about that, the applications that use it. And again, here we saw a vertical spike at about 0.2 seconds, which was interesting. But this is probably due to the delayed ACK timer in TCP, which is right at 0.2 seconds. So if you send a packet and then you didn't get your ACK back within that time, you would resend it. So then you would have 0.2 second inter-packet times. And here's just, again, one more graph of a different TCP connection, inter-packet time CDF, and we see a very similar thing. We have more packets with very small inter-packet times and more variability. And then again, a vertical spike at about 0.2 seconds in both directions. So with these results and this analysis of UDP connections, we conclude that the UDP does not appear to display epoch structure, and instead displays a periodic structure. And in order to model that, it's best to use interpacket times. But however, we did not have enough time to really determine parameters for a heuristic of this model. And so that would be something that would be possible to do in future work. Define an exact heuristic for the model, regenerate the model in the lab, and compare it to the original trace. And then as well as test other models. So test an epoch model just to compare it to our periodic model, and test modeling both sides independently to compare to the periodic model and see which one is most accurate. I'd like to thank Dr. Jaffe, Dr. Icat, Stephanie and Wei. You'll hear from them next. First semester, Stephanie, Wei, and I all worked in a group, and then broke off into our own this past semester. But it's been fun working with all of them. Questions?
Questions?
So anything, you guys have an idea why it's periodic? Just because the video frames are periodic, or there's some timer that's polling?
Yeah.
That's
Sorry.
data, like the Ajax like that?
Right. I think, as far as I think the periodic is from the applications. So if it's streaming, it's sending. The application has a timer in it that's waiting to send each packet. I'm not sure why there's 500-second interpacket times, because that's not streaming per se. And we didn't see that in any of the TCP ones. So I haven't looked into that. That'd be something that'd be interesting. But besides the idea of streaming, we didn't look into why it was periodic.
More research.
Did you look at the size of any of the packets?
Mm-hmm. We did look at the size, and originally when I first looked at it, I did distributions of size in both UDP and TCP, but we didn't correlate the size with the patterns, so with the interpacket times. But almost all the UDP connections that had more than like 10 packets were sending just like full-size packets. So there were a lot of connections that had like 2 packets, maybe DNS connections or something, and those were pretty small. But then the connections with a lot of packets were sending a lot of data. So.
Great. Well, thank you. Okay. Next up, we have Wai Yao, who will talk about a different title. I was going to say it was revisiting, but for most of you, it'll be visiting for the first time. But it has to do with variability in TCP round-trip times. Wai?
Okay. So, hi, my name is Wei, and this is I'm going to present my research today, variability in TCP round-trip times. So before getting to the problem, let's learn about RTT and TCP. So what is RTT? Well, imagine this scenario where you're using your browser and you're doing a Google search. So your browser will send out a request packet to the Google server with your query, and the server will send back a response packet back to you. So round trip time is the time it takes for the response packet to get back to you from the time that you send out that request packet. So why does RTT matter? Well, imagine this other scenario where you're still doing a search, but on a different website. So you found this really well-known Chinese search engine called Baidu. So the Baidu server is located in China. So imagine the round trip time per request is 200 milliseconds. Well, if you have to do a lot of requests, the search requests, then it's going to take up a lot of your time. So let me talk a little about TCP. So TCP stands for Transmission Control Protocol, and it basically provides a reliable and orderly way for the client and the server to exchange packets to each other. So some of the common applications that use TCP include FTP, HTTP, and many email protocols such as SMTP and IMAP. So let me talk about TCP round trip times. So as you can see here on the slides, as you go down the black line, you represent the progression of time. So here's you again, and you're talking to the Baidu server. and let round trip time be 60 milliseconds in this case, and assume that each data packet is 1 kilobyte. And the yellow arrow represents the transmission time, which is the time it takes to submit the data on the wire. So this time you're just doing one search on the Baidu server. So how long would this take? Well, imagine a situation, the first situation, situation A, where we're in a 1 meg network. So the transmission time would be 1 millisecond. So in TCP, before the client and the server can send out packets to each other, they have to establish a connection by what is called a three-way handshake. So what is essentially it is that the client send out a SYN packet to the server, indicating that it wants to send data to the server. And then the server will send back a SYN-ACK packet, acknowledging the SYN that the client sent, and at the same time, wish to send data to the client as well. So to end the three-way handshake, the client send an ACK back to the server, indicating that it received that SYN packet. So after that, the client and the server can start exchanging data with each other. So here we see that there is one round trip time for a SYN and a SYN-ACK, and another one for the data and the ACK, and a half round trip time at the end where the client sent out an acknowledgement acknowledging that it has received the search results from the server. So that would be 2.5 round trip times. And also there are 3 transmission times. So the total transaction time for situation A is 153 milliseconds. Well, a lot of people think that if you upgrade to a faster network, it will cut down this transaction time significantly. But is this the case? So let's look at another situation, situation B, where we are in a 10 meg network. So it's 10 times faster. And so the transmission time is 0.1 milliseconds. But we still have to consider the 2.5 round trip times as well as the 3 transmission times for the transaction. So the total time for B would be 150.3 milliseconds. So as you can see, it doesn't cut down the time that much. So this example shows us that TCP round trip times take up a significant portion in network communications. So back to the problem. Well, first note that RTT is affected by the processing delay of the server, the queuing delay of the intermediate routers, as well as the propagation delay, which is in its definition. And also, we know that RTT equals to 2 times the propagation delay, which is 2 times the distance divided by the speed of light. But here's the question. So within a connection, is RTT constant? Well, according to the formula, it is because the distance is kept constant. But the answer to this is actually no. There is a significant amount of variability in TCP round trip times. And the evidence comes from our own very department. So in 2003, it published a paper called Variability in TCP Round Trip Times. So it basically said that the RTT values within a connection vary widely. But why does it matter? Well, first of all, this contradicts findings from other related researchers that rely on this assumption that RTT is constant within a connection. And second of all, the discovery prompts a search for a better network simulation model, as well as looking for ways to improve the networking technology as well as servers in order to reduce the magnitude and variability of round trip times, so to provide a better user experience. So some of my goal for this research is to first note the variability of round trip times from each data set that I have. So I have one from 2004 and 2008, as well as the data from the 2002 traces that is in the result of the variability in TCP round trip time paper. And I want to do some compare and contrast. And then lastly, to note the trend for RTT variability and magnitude over the years and see how they change. So methodology. So first I collect the UNC network traces from 2004 and 2008. And then for each trace, I analyze each connection, which is between a client at UNC and a remote server that the client is talking to, and collect all the RTTs for each connection. Then I calculate some standard statistics of all the RTTs of each connection and plot them, and compare and contrast these graphs from different years to discover these characteristics and trends of RTT variability and magnitude. So here I have the distribution of the minimum RTTs. So each data point on the graph represents the minimum RTT of a connection. So the green line represents data points from 2008, and the red line represents the data points from 2004. So let's see what we have. So In 2008, 50% of min RTTs are less than 33 milliseconds. So in 2004, 50% are less than 75 milliseconds. And in 2002, 50% are also less than 75 milliseconds. So next we have the 80 percentile. In 2008, 80% are less than 100 milliseconds. In 2004, 80% are less than 180 milliseconds. And in 2002, 80% are less than 200 milliseconds. So we have seen a factor of 2 in the decrease in the magnitude over the years. So now we have median RTTs, and each data point represents the median RTT of a connection. So here we have, in 2008, 50% are less than 33 milliseconds. In 2004, 50% are less than about 100 milliseconds. In 2002, 50% are also less than 100 milliseconds. So that's about a 3 times decrease. So 2008, 80% are less than 100 milliseconds. So note how that compares to the 50% in 2002. In 2004, 80% are less than 300 milliseconds. And in 2002, 80% are less than 450 milliseconds. So that's about a 4.5 times of a decrease. So here we have the mean RTT. So this is the average RTT of a connection that represents each data point. So in 2008, 50% are less than about 50 milliseconds. In 2004, 50% are less than 100 milliseconds. In 2002, 50% are less than 125 milliseconds. So let's see what happens in the 80 percentile. So in 2008, 80% are less than 100 milliseconds. In 2004, 80% are less than 330 milliseconds. In 2002, 80% are less than 500 milliseconds. So that's about a 5 times decrease over the years. So here I have the maximum RTT distribution. So each data point represents the maximum RTT of a connection. So in 2008, 50% are less than about 56 milliseconds. And in 2004, 50% are less than 100 milliseconds. In 2002, 50% are less than 250 milliseconds. So we have seen about 5 times decrease. So in the 80 percentile, we have, in 2008, we have 80% are less than 130 milliseconds. 2004, 80% are less than 500 milliseconds. And in 2002, 80% are less than 1,000 milliseconds. This is 1 second. So we have seen a 10 times decrease in the magnitude here. So that's not all. So here I have the complementary distribution of the maximum RTTs. So to highlight the tail or the last few percent of the data set. So let's see what we have. So in 2008, 10% are greater than 300 milliseconds. So that's not too bad. In 2004, 10% are greater than 1,000 milliseconds. So you think that's bad. But in 2002, 10% are greater than 3,000 milliseconds. So that is 3 seconds. So in 2002, 10% of all the RTTs are greater than 3 seconds. That's a lot. And also, the magnitude has decreased over 10 times over the 6-year period. So now let's look at some overall comparisons to see the degree of variability among each data set. So here we have the 2002 distribution and see how wide the gap is between the minimum RTT and the maximum RTT when the mean and the median are about the same. And notice how, on average, 90% are less than 1,000 milliseconds. So in 2004, you can see that this gap has closed up quite a bit. And the magnitude, on average, are also smaller. So 90% are less than 100 milliseconds. So in 2008, we can definitely see the gap almost disappear from that. And the magnitude has decreased even further. So 2002, we have still seeing the tail have some variability. And so it's 2004. But in 2008, the gap almost closes as well in the tail. And the difference between the max and the mean and the median are basically non-existent. But these only shows that there is variability in round trip times overall. And this doesn't really show that there is a variability in round trip time within a connection. It turns out that there is a pretty simple measure to test to see if there is a variability within a connection. And it's called the max to min ratio. So what this is for each connection, you take the maximum RTT and the minimum RTT, and you divide max divided by min and get a ratio. So ideally, if round trip time within a connection is constant, then we will see 1. But what is the case in reality? So here again, we have a distribution of the max to min ratio. So let's see what we have. So in 2008, 50% are less than about 1.1. So that's pretty constant. In 2004, 50% are less than about 1.3. So that's not as good, but still pretty constant. But in 2002, 50% are less than 3. So that's pretty big already in the 50th percentile. So let's see what we have in the 80th percentile. In 2008, 80% are less than 1.5. And 2004, 80% are less than 3. But in 2002, 80% are less than 8. So that's basically saying that the max RTT is 8 times the size of the minimum RTT. So this is a pretty huge variability. But that's not all. So in 2008, 90% are less than 3. So now know how that compares to the 50% in 2002. In 2004, 90% are less than 6. But in 2002, 90% are less than 16. So not only did the variability go down by more than 5 times over the 6-year period, but in 2002, the variability is very big. So that's a thing to note. And also, the average ratio went from about 4 in 2004 to 2.3 in 2008. So this tells us that the variability within a connection definitely exists, and that it has decreased pretty dramatically over the years, by about 5 times from 2002 to 2008. So these results that I have today show that the variability within a connection has decreased over the years, and so has the magnitude of RTTs. So it's very likely that both of them are attributed to the fact that there is an advancement in networking technology and servers, providing a more stable timetable for processing and transmitting the data. And also, having more servers closer to us during the last several years also helped reduce the magnitude of the RTTs. But we know that we still cannot overlook this variability, even with knowing how small it is in 2008, because there's a lot of traffic in the network these days, and even a small amount of variability matters on a large scale. So this is my presentation, and thank you for listening.
And of course, last but in no means least, we have Stephanie Zolivar, who's going to talk about characterizing modern web traffic. This is just to build anticipation.
Sorry. Oh, God. Okay. I'm Stephanie Zolivar, and I'm really hungry. So try to make this quick. So my project has to do with characterizing modern web traffic, and I was supervised by Kevin Jaffe and Jay Akat over there. And so some motivation for my project is just that web traffic and the way we use the web has changed a lot in the past decade, and it's good to keep modern characteristics updated such that we can have accurate data for networking test beds and people making applications and people managing networks, and just it's good just for science. So that's why I did it. And so what I did was I did a statistical analysis of an hour-long TCP trace, and I used the one from 2004. And an important thing about what I did is I'm looking at sort of the application layer, whereas Rebecca and Jay were looking at the transport layer, Rebecca and Wei. And so, but I only looked at the TCP layer, so I was only looking at the TCP headers, and I was using that to infer things about the application layer, but I wasn't actually looking in the application data. So a big thing about my methodology was I looked in the headers to look at the port numbers, and I used the port numbers to identify different protocols. So the 2 protocols I looked at most closely were HTTP and HTTPS. And you can see from this table, there are about 100,000 HTTP connections and about 3,000 HTTPS connections. Yeah, okay, so just overview of HTTP and HTTPS. HTTP is a widely used protocol for the web that consists of request-response pairs. And then HTTPS is actually built on top of HTTP, so it has the same request-response structure, but it uses TLS to actually encrypt all the data being sent over it. So it's used in like a subset of the web where data is sensitive and needs to be protected, like email and banking and Facebook and stuff like that. So this is just an overview of what a connection looks like. So we've got the client sends a request, server sends a response, and this can actually happen multiple times within the same connection. So this is just one connection right here with two of these request-response pairs. And some important parameters of this connection is we looked at the server think time and the user think time. So the server think time is just the amount of time that the server has to spend processing a request before it can send a response. And the user think time is the amount of time before the user sends a new request after receiving a response. So that can either be user interaction, like the user clicking on a new link or something, or it can be an automated request being sent based on the data sent by the server. And then just another bit of terminology to reiterate what Rebecca said is this is an epoch is a request-response pair. So this connection right here has two epochs, the first one and the second one there. So one of the first things we looked at in the data set was distribution of the number of epochs per connection. So this plot here shows that most of the HTTP connections had one epoch, whereas most of the HTTPS connections had two epochs. So in particular, 75% of the HTTPS connections had two epochs. And this is really weird because of the TLS handshake. So if you remember, HTTPS is TLS over HTTP. So an important part of that is it encrypts all the data being sent back and forth. So the way it starts out is it starts out with this TLS handshake, in which they exchange sort of authentication and key information. So they're just negotiating session keys for the connection. And this handshake actually consists of two epochs. So all these connections here that had two epochs didn't go past the TLS handshake. So they didn't actually get to this part down here where they're sending actual data. So that's really weird. And at this point, we can only speculate as to why that happened. But one speculation is that it could theoretically be like a DOS attack, like someone who's just like trying to establish the connections and then not do anything else with them. But that's kind of far-fetched anyway. So.
People would never do that.
Yeah, that doesn't make sense. So there's that. And so we also looked at other properties. So keeping that in mind for the rest of the data it has big implications for the rest of the data. So it's good to keep in mind. So this plot is for the distribution of the amount of data transferred over entire connections. So for the two protocols. So an important thing here is that 30% of the HTTPS connections transferred around 1,000 bytes. And that's likely an artifact of the TLS handshake because of the canonical packet sizes, or request sizes and response sizes. And then, so once you get beyond this TLS handshake range, the secure web actually transferred less data per connection. And we can actually see this also in the tail of the distribution. Again, so the lighter distribution being on the left there means that the HTTPS connections transferred less data than the HTTP connections. So we also looked at round trip times for the two protocols, and this is the same round trip time that Wei is looking at. It's the transport level round trip time. And what it shows is that HTTPS had faster connections. There's a factor of 2 difference in the medians, and so could possibly be because of better provisioning of servers in where HTTPS is deployed. So another thing we looked at is server think time. So server think time, again, is the time it takes for the server to send a response once it's received its request. So what this shows is that HTTPS, with the lighter distribution here, is actually taking less time to process a request and send a response. And this is kind of weird because all other things being equal, we would expect encryption to add overhead to the HTTPS connections. And so therefore, we would think that the server think times would be larger. But they're actually smaller. And one explanation for this, again, is the TLS handshake, because there's not a lot of processing that has to be done on the server side to just to respond during the TLS handshake. And so we see a similar thing with user think times. There's a large difference in the medians, and it's it's not what we would expect given that encryption adds overhead. So then we also looked at sort of the data being transferred over these connections. And so we looked at request sizes for HTTP and HTTPS. So this is the request sent from the client to the server. And one thing here is to look at is all this discretization happening up front. So about 25% of the HTTPS requests were 100 bytes. And again, that's probably part of the TLS handshake. But then once you look out past that region, you look at the crossover point area, the HTTPS requests were larger than the HTTP requests. So that's interesting. And then the response sizes, you see the opposite thing. The HTTPS responses were smaller than HTTP responses. And then you also see more canonical or discretization artifacts here, both in HTTPS and HTTP. And this is actually like a way bigger difference than in the previous slides. It's almost a factor of 10 in the difference in the medians. Okay, and then so this is within HTTP. It's request versus response sizes. So what we see is that requests are significantly smaller than responses. So 97% of the requests were less than 1,000 bytes, whereas the responses go up to 10,000 bytes. And so this pattern is actually, you see the same pattern in HTTPS when you look out past this crossover point around, I guess that's like 8,000 bytes or something. So you see the requests are smaller than the responses. But then you also see the discretization actually almost lines up sort of at the beginning there. So overall, the HTTPS connections transferred less data, had faster connections, and had smaller think times. And one way we're explaining this is the TLS handshake because of the small packets being sent back and forth without a lot of work having to be done. And then also just better provisioning in sort of the subset of web traffic that represents secure traffic. And so some future work is to factor out the TLS handshake to really compare the application data being transferred back and forth, and then just to repeat this on newer traces.
Great. Questions for Stephanie? In the back.
Who's that guy in the back?
Good. That's nothing.
Some part of the research has to stay secret. That's all. Go ahead.
So, factoring out the TLS handshake,
Mhm.
is that the same as taking out these anomalous 2-epoch?
So the TLS handshake, so the TLS handshake should be happening on all of the HTTPS connections, not just the ones that only had 2 epochs. So it would be, we could just take out those, throw out those because they're weird, and then just see what the rest of them look like. And then another approach would be to factor out the first 2 epochs of all of the connections.
Other questions? Well, let's thank Stephanie. And I'd like to thank everybody for showing up. I hope you enjoyed the presentations. And for those that are not graduating this year, as they say, consider doing this in your spare time for next year. And now, without further ado, we can transition outside for the refreshments of unspeakable awesomeness.